So we're talking about the demodulation of the signal in the frequency domain. So in the frequency domain, it is how it looks like. So when you take this modulated signal and multiply it with cos omega ct, it means that whenever you multiply any signal with the cos omega ct, it shifts the signal with some fc amount right and some fc amount left. Okay? So same thing will happen here. We have this signal when you multiply it with cos omega ct, it will shift this complete signal left and right by fc amount. So when it shifts this thing left by fc, you will get this. You see, it is centered around -2 fc. Here it was centered around -fc. Here it is centered around -2 fc. When you take this one and shift it left by fc, it will drop at dc, right? This is already centered at fc. When you shift it left by fc, it will come at dc, so it will look like this. Okay. Now this is the thing you'll get after shifting left. When you shift right, you take this signal and shift it right by fc. So it is centered around -fc. When you shift it right by fc, it will center around 0. And again, you'll get the same thing, kind of, yeah. And when you add this green and this red one, you'll get this signal, this red one. Okay. And when you shift this right, you'll get this one. Okay. So if you see this was the message. Message was something like this, a triangular waveform. We modulated it. After the modulation, it looked like. Then after that, at the receiver side, we are trying to demodulate it. First step is to multiply it with cos omega ct. After the multiplication of cos omega ct, it moved from here to here. And then after that, we will pass it through low pass filter. So when you pass it through low pass filter with which looks like this kind of filter, it will pass this DC signal or signal centered around DC, and it will reject the signal centered around higher frequency. So after passing through low pass filter, you will get this signal, which is same as our message signal. Okay. So this is how the demodulation is working in the frequency domain. Go to the next slide. Now, till now, whatever we have discussed, that is what we call it as a double sideband. And there is one important thing to note here is that when you take the message, see the message, whatever the information content is there at this side, same information content is there on this side. Okay, if you remember from the Fourier transform property that if you have any real signal, its magnitude spectrum will be even function of omega or f, or its phase spectrum will be odd function of f. So whatever the information that you have at the positive frequency, the same information you'll get from the negative frequency also. Okay. So when you modulate it and get this signal where you have both upper sideband and the lower sideband, both upper sideband and lower sideband are pointing to the same information content. So it means that whatever the information that we have in this side, same information we have on this side. Okay. And from there, this single side band modulation concept arises. So instead of sending the both upper sideband and lower sideband, what we can do is we can remove the one of the sideband and send just one of the sideband. Okay. So either you can remove the upper sideband and just send the lower sideband, or you can remove the lower sideband and just send the upper sideband. Now, what will happen with this operation is that your bandwidth of the modulated signal will go down by half. Okay. So in the case of DSBSC, the bandwidth was too big because it was ranging from fc minus b to fc plus b. But if you remove half of them, let's say we are removing USB, in that case, signal will vary from fc minus b to fc. And this range in the frequency is equal to B, and it means that the bandwidth of the signal will become B. Okay, so that is a very like good benefit that we're getting out of the single sideband modulation, because this spectrum are very costly in general. this spectrum, if you have might have heard that government auction this spectrum, and generally this spectrum are very costly, so we want to use it very efficiently. And one way is to remove the DSBSC and use the SSB. Okay, so once you go from DSBSC to the single sideband modulation, you will get the benefit in terms of bandwidth utilization, and here the bandwidth will go down by 50%. So that is the another analog modulation. So till now we have seen three kind of modulation. One was the AM, one is the DSBSC, and now this is the SSB modulation. Anyone has any doubt here? Now let me go to the next slide. Now, how do we demodulate the SSB modulated signal? So let's say we have the only upper sideband SSB modulated signal, and I want to demodulate it. So the demodulation circuit will be same as the DSBSC. So in the DSBSC, we took the modulated signal, multiplied with cos omega ct and pass it through low pass filter. Right? Same thing we will do here. We will take this USB signal, multiplied with cos omega ct. So we know that when you multiply the DSBC signal with cos omega ct, the signal will shift left and right. Okay. So once it shift left, so this portion, when it shift left, it will go here. And when this signal shift left, it will come here. Okay. Now when this signal shift right, it will go here. And when this signal shift right, it will go here. Okay. Now you can just apply a low pass filter and filter out this portion and this portion, and you'll get back the message. Okay. So you see the demodulator is same as the DSBSC demodulator. We don't need to do anything extra here. So just take the same demodulator that we have the DSBSC and use it. Okay. The same thing is for the lower sideband also. If you have the lower sideband modulated signal, multiply it with cos omega ct first, and then pass it through low pass filter, and you will get back the original message signal. Okay. Let me go to the next slide. Now, I will just quickly go through this Hilbert transform, and the motivation here to use the Hilbert transform is to generate the SSB signal. How do we generate the SSB signal? So what is the Hilbert transform? So in the time domain, the impulse response of the Hilbert transform is given as 1 by pi t. But in the time domain, you will not be able to appreciate this Hilbert transform. Let's see in the frequency domain. So in the frequency domain, when you take the Fourier transform of this Hilbert transform, it looks like this. Its magnitude spectrum will always be equal to 1. And the phase spectrum of this Hilbert transform will either be 90 degree or minus 90 degree. If frequency is positive, minus 90 degree. If frequency is negative, then it will be plus 90 degree. Okay? So you can say that in the magnitude wise, this Hilbert transform doesn't do anything. So if you give some input in the magnitude spectrum, it will remain same. But in the phase spectrum, it will shift the phase of the signal by 90 degree. Okay, so that is the important property of the Hilbert transform. It is act as a kind of phase shifter. Let me go to the next slide. Okay. So let's say we have a signal, and it's in we have a signal and it is equal to cos 2 pi at. Okay, and this we are giving it to the Hilbert transform, and we want to find out what will be the output of this filter. So we know that this Hilbert transform is kind of phase shifter, which shift the phase of the input signal by 90 degree. So when you take this cos signal, shift phase by 90 degree, you will get this sine 2 pi at. Okay. So this is the how the Hilbert transform works. It just take the signal and shift it its phase by 90 degree. So how do we generate the Ssb signal? So that's where this Hilbert transform comes into picture. You have the message, okay? Take this message and multiply it with cos omega ct. You will get empty cos omega ct. Okay. Now take this message and pass it through a Hilbert transform. Let's say you are getting MHT. Okay. And then you have this cos omega ct. This also you pass it through the Hilbert transform. You'll get sin omega ct and multiply this too. So with this, you'll get mh sin omega ct. When you add this empty cos omega ct and mh sin omega ct, whatever the signal that you get here, that is actually the Ssb signal. This is how we generate the Ssb signal. So here, the generation of the Ssb is kind of complex than the DSB-SC. Okay, so that is a trade-off here. Here we are able to reduce the bandwidth by 50%, but the trade-off is that the transmitter circuitry or the modulator circuitry is now complex than the DSB-SC. So this is the phase shift method of the Ssb generation. There is one more method that we call it as a filter method. That is pretty easy. Just take the Ssb signal and pass it through a low pass filter. So let's see what happens. So this is the DSB-SC signal. When you pass it through low pass filter with cutoff frequency FC, what will happen that it will reject all the signal outside this rectangular and it will just pass the signal which is inside this rectangle. So once you pass the signal through this filter, you will get this signal which is just a lower sideband. It doesn't have any upper sideband. Similarly, if you want to send the USB signal, pass it through the high pass filter. So when you pass it through high pass filter, it is how it is going to look like. This is the high pass filter. It will pass only the high frequency content which is above the FC and reject all the content which is there from minus FC to plus FC. Okay. So when you pass it through high pass filter, you'll get this signal. When you pass it through low pass filter, you get this. So this is the phase shift. This is the filter method to generate the Ssb signal. Okay. This question is based on the AM signal. So let's say we have an AM signal and it occupies a frequency in the range from 395 to 405. Okay. So its spectrum is something like this. It is there from 395 to 405. And we want to demodulate it and we want to find out how to demodulate it. And the four options given. First is envelope detector. Second one is multiply the signal with 395 kilohertz local signal. Third one is multiply the signal with 405. And last option is to pass it to the low pass filter with cutoff frequency 400 kilohertz. Now let's explore this. So we know that if you have an AM signal, we are talking about the AM signal, which looks like this. Okay, it has A plus MT and then cos omega CT. This is the AM signal. And we know that to demodulate it, we take this signal and pass it through the envelope detector. Okay. So this A option will be the correct one. People get confused with these options because sometimes they think of this signal as a DSB-SC signal. Instead of thinking of this as a AM signal, they think of this as a DSB-SC signal, but we know that this is not a DSB-SC signal because it is mentioned in the problem. It is amplitude modulated signal. And because of that, whenever you have the amplitude modulated signal, we will demodulate it with the help of the envelope detector. Now let's explore the other two options. Multiply it with 395 kilohertz local signal. Okay. So if you multiply it with 395 kilohertz local signal, it will not be able to demodulate properly because here the signal is centered at 400. So if you want to recover it with the help of the DSB-SC demodulation method, you should multiply it with 400 kilohertz, not the 395. So that's why this option and this option are wrong. The last option is to pass it through the low pass filter. That also is also known because after passing it through low pass filter, you just get this LSB and this LSB, lower sideband only. You will not get the actual message. Okay. But if in the option, let's say it was given as multiplied with 400 kilohertz, then it will be correct. But that option is not here. Instead of that, we have been given option as another detector. So this is the correct option. Okay. But if the option were something like this, multiplied with 400 kilohertz, that would have been correct option. Okay. So